So I didn't give one proof on the last class. I told I'll do it later. I will send you that. It's very simple actually, but very tricky as well. Okay, that is, suppose the statement P is that there exists a function f from a to set of all natural numbers if such that f is 1 1, such that f is 1 1. Okay, if p is p is a statement saying that there exists a 1 1 function between from a to n, and q is a statement that says there exists a onto function, onto function g, onto function g from set of all natural numbers to set a. So P says there exists a 1 1 function from a to n. Q says there exists a onto function from n to a. Now what I said was that P and Q are actually equivalent statements. That is, if P is true, Q is true. If Q is true, then P is also true. So let's try to prove that. I didn't prove it in the class, but I said I'll give you a proof later. So I thought about it and derived the proof. It's very simple actually. So let's assume that P is true. Okay, so let P holds true. Let's P is true. P holds true. That is there exists a function. There exists a 1 1 function f from a to n, set of all natural numbers. So if this function exists, then I have to construct a function g from n to a, which is onto. It constructs a g. So how do I construct it? Using f, I'll construct the function. So clearly because f is 1 1 function, clearly what we know is f inverse of any natural number n is either empty set or a singleton set So f inverse n is for, you take for the singleton for all n. This is true for all n. See, f may not be onto, but f is 1 1. Therefore, if you take a element on the codomain n and try to see its pre-image can be empty also. When there can be element in the set n, so there can be a natural number whose pre-image doesn't exist. But if it exists, it's only singleton set. Okay, singleton, because f is 1 1. Because f is 1 1, two elements of A cannot be mapped to same element in n. That's the nature of 1 1, definition of 1 1. So therefore, let what we do for this is, I'll define a g like this. I'll define a g from n to a. How I define is g of n, hold on. So how do I define this g is g of any element n. Okay, so g of n, I should define g of n. Okay, for every element in n, in the set n, as, so this map g is whatever f inverse of n, that singleton set is there, that value is f inverse of n if this is non-empty. Okay, if f inverse of n, hold on, I'm not writing it clearly here, I'll write it again. G of n is that set as f inverse of n, which is element of A, if f inverse of n exist, because it cannot be exist because f is a one function, it's not onto function. If it exists, it is f inverse of n. If it doesn't exist, what? If f inverse of n does not exist, or it's an empty set, or it's an empty, we can write it as an empty set. It is a empty set. If it is empty set, then you can pick any A, okay? Pick any A belongs to A. Okay, for any A belongs to A. So now check this function G. So f is a function from A to n. F is a function from A to n. A to n we have f. And G is a function from n to A. We have function from G from n to A. Now if you see here, every element of A has a pre-image. So now we'll check that this G function is onto function. How to check that G is onto function? You take any random element, any arbitrary element. Okay, let A belongs to A. Be arbitrary. This is arbitrary element. Arbitrary. Then we can show that there exists a natural number in set, a natural number in n, which under G it maps to A. Its image is A. So it's clear that directly if A belongs to A, then clearly f of A belongs to n, and f of A exists always because f is one function and it's a function, therefore f of A exists in n. So now take this f of A and take f inverse of f of A. F inverse of f of A. This is actually G of A. G of f of A. This is actually G of f of A. Okay. But f inverse of f of A is always A. And because it's one function, it's only singleton set K. So therefore, we got an element f of A in n. If you apply G on it, you get the element A. Thus, for every element A belongs to capital A, we have a candidate in the domain n, which takes that candidate to A under G. Thus, thus G is onto function. So the other way around. So what we proved is that P implies Q. So P implies Q. If P is true, we proved Q is true. The next video, I will show you if Q is true, how P becomes true. Okay, thank you.